So welcome to our fourth lecture, Dealings with Solids and Liquids. In our last lecture, we had finally managed to condense our gas into the liquid and noted that the liquid has a vapor pressure, which is the loss of higher energy particles off the surface. Now that's an interesting point to note. You're talking about losing the higher energy particles. What's that doing for the average energy of the remaining particles in the solution? Well, obviously, if you're losing the higher energy ones, the remaining ones have lower average energy. In other words, evaporation is a cooling process. That's why when a nurse swabs your hand with rubbing alcohol or alcohol, it feels cool, because the liquid is evaporating off your skin, taking energy away. And so you get a cooling effect from being wiped with alcohol by a nurse. On the other hand, you cool the liquid enough, it drops into a solid. And so now we're going to start talking about solids. Solids are 3D arrays. What's different between different solids is what is making up the 3D array. And so we basically run into four kinds of solids: molecular solids, ionic solids, metallic solids, and network solids. The first kind of solid we're going to talk about are molecular solids. In molecular solids, a 3D array is made up of molecules. The molecules make up our nice 3D array, and they're held together by the intermolecular forces. But the intermolecular forces are relatively weak. That means it would be fairly easy to move one of those rows back and forth. And so molecular solids tend to be low melting materials. And in the same way, of course, breaking up that array, and that is getting the particles back into motion, also tends to be fairly easy. So they also tend to be low melting materials as well. The most obvious way you can tell that a molecular solid has vapor pressure is it usually has a smell. That is, your nose picks up the molecules that have gotten up into the gas phase and you can smell it. Molecular solids frequently have aromas to them. The most conspicuous example, of course, is a molecular solid with a vapor pressure is dry ice, that is solid carbon dioxide. There's a reason it's called dry ice. It's because it doesn't melt, at least not at atmospheric pressure. Instead, it simply goes directly into the gas phase. We talk about it subliming. Carbon dioxide, solid carbon dioxide, has a vapor pressure of more than 1 atmosphere at room temperature. So the dry ice just disappears. It evaporates directly in the gas phase without bothering to melt. The next kind of solid we run into are ionic solids. And in this case, we actually have two 3D arrays. We have an array of cations and interlocked with it an array of anions. In the ionic solids, we get this every other placement kind of position, where each of the cations has as its nearest neighbors anions, and each of the anions has as its nearest neighbor cations. And so we get an alternating pattern of cations and anions. And what's holding these together, of course, are the Coulombic attraction between the ions. And the ions like that. And so these tend to be hard materials. You might consider what would happen if you tried to shove one of those rows over. It would resist. So ionic compounds tend to be very hard materials. But if you did shift the row over one spot, what would happen? Well, it would bring cations opposite cations and anions opposite anions, so it would fall apart. So ionic compounds tend to be hard, brittle materials that break rather than deform. And of course, the ions like sitting right where they are. They don't want to go back into motion. So ionic solids tend to be high melting materials. And finally, of course, they're not good conductors of electricity. But you have to be a little careful about that. They're not good conductors of electricity as solids because the ions are all locked in place. And again, they don't want to go anywhere. But if you melt ionic compounds and or put them into solution, they in fact become very good conductors of electricity because now the ions are in fact free to move around. And finally, of course, what is the chances that the ions will simply drift off into the gas phase? And the answer to that is zilch. So ionic solids are not going to have vapor pressures. The third kind of solid we run into are metallic solids. And a metallic solid is made up of a 3D array of metal atoms. And what's holding the 3D array of metal atoms together is what is called metallic bonding. Metallic bonding is kind of a special case. Consider a zinc atom. A zinc atom all by itself consists of the nucleus with its protons and neutrons around it, and then 30 electrons. And where are the 30 electrons? Well, the first 18 are of course in the same arrangement as argon, so they are packed in close to the nucleus. The next two fill in the 4s orbital, and that's starting to fill the 4 level, so that's a long way from the nucleus. And then the next 10 are in the 3D shell, which is completely full and therefore packed down with the other electrons from the argon inner shell. So we have a nucleus, a nice tightly packed array of 28 electrons, and then finally the 2 valence electrons in a large orbital outside the zinc. So what's going to happen when we start condensing zinc atoms as a solid? Well, what happens, of course, is they're going to come together until the electrons begin interfering with each other. But we said 28 out of the 30 electrons in the zinc are packed in nice and tight. And so those, in fact, are going to be what's going to decide how close the atoms get together. And so the electrons in those outer orbitals are going to end up overlapping. And so the arrangement of the electrons we see in the zinc as a solid is the nucleus forms a nice 3D array. The inner packed electrons decide how close the nuclei are, and then those valence orbitals are all overlapping each other. And so that becomes a question. Which atom is one of those electrons associated with? Well, it's in the different orbitals of 3 or 4 of those zinc atoms. And so this is what we're talking about when we're talking metallic bonding. We talked about covalent bonding, but covalent bonding is very specific and very directional. It's 2 electrons holding 2 atoms together. This is very diffuse sharing of electrons. All those zinc atoms sort of hold on to all those valence electrons, but none of them hold them particularly, and they're not associated particularly with any one of them. And that's what we're talking about when we are talking about metallic bonding. This kind of diffuse, wide sharing of the electrons. An immediate consequence of this, of course, is what would happen if we shoved one of those rows over? Well, basically nothing. It'd look the same. So metallic solids are flexible materials. They bend easily without breaking. On the other hand, breaking up the array depends very specifically on the metal. Some metals, like mercury, is a liquid at room temperature. All the alkali metals have melting points under 100 degrees. Meanwhile, tungsten melts at 3,700 degrees. So the metals melt all over the place as far as melting point goes, and so they have a wide range. Generally speaking, metals tend to have higher melting points, but some of them have really low melting points. The most significant thing about, of course, the metals is they are in fact good conductors as solids, because of course it's easy to move those electrons because they're already sort of spread out throughout the whole structure. So the metals as solids are good conductors of heat and electricity. And again, what's holding them on the surface is the metallic bonding, and that has to be very specific for the metal. And while in general the vapor pressures of metals tend to be extremely low, nonetheless they do have some vapor pressures. Mercury, for example, has a significant vapor pressure at room temperature, although it's very slight. Which brings us to what is a very special case, a network solid. And what's important about a network solid? What makes a network solid is it's a 3D array of atoms that are all bonded to all of their neighbors. That is, it's an extended array of bonding. If you start out with just carbon in the form of graphite at room temperature, graphite actually forms sheets of 6 carbon atoms bonded to each other in circles. And actually that diagram is a pretty good representation of graphite. It's in sheets, and the solid is simply layers and layers of those flat sheets. Looking at that structure, you can see that in fact there's a certain amount of open space in there. It is not absolutely packed in as tight as possible. And that makes an interesting phenomenon occur. If you take the graphite and push down on it really hard, that is, exert a tremendous amount of pressure on it, you can actually force those carbons closer together, and you get the array at the right side. And in that array, each carbon atom is bonded to the 4 carbon atoms around it. And each of those 4 carbon atoms are bonded to the carbon atoms around them, and etc., throughout the whole structure. And in fact, that of course is a diamond. And a diamond is in fact a macroscopic molecule. It's all one set of atoms that are all bonded together. And what kind of properties do we get out of this array? Well, first and foremost, how easy is it going to be to shove one of those rows over one? Well, it's going to be almost impossible. You have to break every single one of those bonds that are holding those rows in place. So network solids aren't hard, they're extremely hard. They make up all the hardest materials that are known. And that's just moving one row. To break up the whole array, you'd have to get break all the bonds in that whole network. And that would take huge amounts of energy. So network solids aren't high melting, they're extremely high melting. Not surprisingly, they are poor conductors of electricity because all their electrons are in fact tied up in bonding. And so while they're extremely hard and extremely high melting, they are again really poor conductors of electricity. And finally, of course, what is the possibility of any of the atoms simply wandering off into the gas phase is zilch. They're not going to have any vapor pressures. And that concludes our discussion of Chapter 14. We've already done Chapter 15, and since we're running out of time, we're going to skip over 16 and go on to Chapter 17 instead in the book. See you next time.